So a while ago, I found this PS2 mouse lying around. Some 15 years ago, these were pretty much the standard of computer mice, and keyboards use PS2 as well. But these days, you really don't find any devices that even support PS2, especially laptops. Though it has been continued to be used as a legacy port on some motherboards. But what I wanted to do today is to try and see if I could get this mouse to communicate with an Arduino board. This is what a PS2 connector looks like. This is the mouse connector, and this is the keyboard connector on this cable that I have right here. So if you can notice, it is a 6-pin mini DIN connector. So I didn't want to cut up this connector right here, so I actually bought some of these proper connectors. So you can see that the PS2 connectors, or these 6-pin mini DIN connectors, look like this, and that will allow us to plug the mouse into it. So now we can actually have a point to solder to on this connector. So when we look at this connector, we have to realize what's actually going on here and the pins that are being used and what they're being used for. So looking in from the female side, so we're looking at kind of head on like this, you can see that there are 6 pins, but only 4 of them are used. Going in this direction, we have the clock, ground, data, and 5 volts, with these 2 being not connected. If we just look at this, well, it's pretty obvious that 5 volts is going to go to 5 volts to supply the power to the mouse, and the ground is going to go, well, to ground of the Arduino board. That leaves us with 2 additional lines, the data line and the clock line. So these 2 are going to be used for communication purposes. As I have soldered up the connector, you can see it is soldered in the way as pictured. So we have our 5 volts, ground, and then we have our data and clock in green right here. And we have an Arduino board like that. So now we can wire up the connector to the Arduino. So we want ground to go to ground. 5 volts has to go to 5 volts. And then our data line could really go to any pin, but we're going to have the data line go to pin 6, just for convenience. And that is a pin that's available. And then our clock is going to go to pin 5. So this is the circuit that we have right here, and this is all we're going to be actually needing to wire up. And then of course we could get our PS2 mouse and just plug it in as if it were on an actual motherboard, and it will go in like that. So here's the completed physical circuit. Now of course we have to program the Arduino in order to actually communicate with the mouse, receive data from the mouse, and process it into something that we could use. So in order to actually use the mouse, it requires an understanding of the PS2 protocol. So unlike USB, PS2 is actually relatively simple. PS2 is only a single bus that either goes to a mouse or a keyboard, and the ports are either designed for a mouse or for a keyboard. So we only have to make it work for the mouse, and it works in a specific way. Really the only difference is that some mice have a scroll wheel and some mice don't. So that will affect the bytes that we're going to use. For this video, we're just going to set up the mouse to not use the scroll wheel, just because that makes the setup a bit simpler. PS2 is interrupt driven. So the mouse is actually doing most of the work controlling the bus. So in order to actually get the mouse to work, well, when we first plug it in, it's not going to work because it's not enabled yet. So we have to have the computer, or in this case the Arduino, send a command to the mouse in order to enable it. The command to reset the mouse is 0xFF in hex, and to enable the mouse is F4. You might not need this reset, but we're just going to do it anyway. It should reset upon power up, but you definitely do need this enable, and that's to get the mouse to send data. So now we know we have to enable the mouse in order to get the mouse to send data. The clock and data are always going to be pulled high by the mouse in any circumstance that we are not either receiving data from it or writing to it. So that's the idle state is clock and data are both high. So in order to write to the mouse, we're going to have to bring the clock low, and that's going to disable the mouse from communicating. All right, so once we've done that, we have to bring the data line low, and that's going to request the mouse to allow a transmission to be received. Once again, the mouse is controlling the flow of data. We're just requesting it from the host to give the ability to send a byte. And after that, the clock has done its job, so we can pull it high. So what this pull high means is that on the GPIO of the Arduino, the clock here is going to be set to an output, and here we're going to set it back to an input with a pull-up resistor. And now we're going to wait for the mouse to bring clock low again on its own, because we're pulling it high, but the mouse itself is going to pull the clock low, and what that means is that the mouse is now ready to receive a command. And what we can do is, since PS2 is a serial connection, we can shift out a byte from the least significant bit to the most significant bit on the low clock cycles. Just because of the way PS2 is formatted, there's also a parity bit, which is going to be odd. So as long as there is a odd number of ones, the mouse will know the data is good. So while we are shifting out the data, we are going to keep track of how many ones is in the byte that has been sent. And if there's an even number of ones, we're going to add a 1 to the parity bit. If there's not, then the parity bit will remain 0, and that will be shifted out in either case. So we've shifted out all 8 bytes plus the parity bit. So now once the information has been sent, we can wait for data to go low again, clock to go low, and then data will go high, clock will go high, and then we are done writing a byte to the mouse. So once again, in order to get the mouse to work, we're going to have to send this, which is 0xFF in hex, and then we're going to have to send F4 to enable the mouse. And that basically means we are going to have to repeat basically this algorithm, or this pseudocode, I guess, twice. So now that reset and enable have been sent to the mouse is now capable of sending data. And the mouse sends the data when something happens to it. So PS2 is interrupt driven, so basically the mouse will send data when it moves or a button has been pressed. The first bit sent from the mouse is going to be the start bit, and it's going to always be 0. If you're using the mouse with an interrupt, you can tell, because whenever data goes 0 from 1, when it's been 1 a long time, that means that the mouse is getting ready to send data and you can receive it. Then the 8 bits will be shifted out, and this is the data actually from the mouse, and we'll get into what this data actually means as well. And then there's a parity and a stop bit. This is how the data is formatted, but this is one packet, and the mouse always sends 3 packets at a time. The first packet sent by the mouse is going to be like this, and this bit is the least significant bit. It's going to be left click. So if the left button is clicked, this will be 1. If the right button is clicked, this will be 1. If the scroll wheel is clicked, this will be 1. This is always 1. And these are the most significant bits of the movement of the mouse, which is over here. And these are the overflows. This is the movement of the mouse. You could see that these are separate bytes. So this is the first byte, second byte, and third byte. And these are 9-bit 2's complement numbers. So that allows us to have positive y, negative y, positive x, negative x. And that's formatted like this. And once again, the most significant bit is over here on this byte, because these are only 8 bits each. So to have 9-bit 2's complement, you need to store the bits over here. And this is going to be the sign. So if these are 1, then it's negative, and you got to reverse the 2's complement format. So now let's get into the code we're actually programming the Arduino with. So first we have our pins, clock and data. And here we have some function declarations to write to PS2 and to read from PS2. And here what we're doing is we're writing out the FF to reset the mouse, and then we're writing out this to enable the mouse. And what happens is the mouse is going to respond whenever we write to it. So with the reset command, it should give us 3 different bytes. The first packet sent out is going to be FA, or it should be. This is going to be the acknowledge. And whatever you write out to the mouse, whatever the command is, it's always going to send the acknowledge to verify it's been sent and received. So then it's going to realize, oh, we're going to reset the mouse. So it's going to do a self-test, and the result of that should be AA. And then it's going to give the mouse ID, which should be 0. And then, of course, we're going to set the mouse to enable, and the result of that should be FA for the acknowledge, and that's all that's being sent there. I had a lot of trouble getting this program to work because of this. So yeah, it has to be unsigned logged int, otherwise there are overflow issues when we do bit manipulations and when we print from serial, oddly enough. So yeah, use unsigned log int for your reads. Well, the data that's read out is not actually the byte. So we're going to have to do some bit manipulations, and we're going to have to take off the parity start and stop bits. So now we're just going to print up the startup sequence, and this is just going to print out what we've done before. The simplicity of this code, we're not actually using interrupts here. We're just going to use polling and just pull the mouse. Busy wait until the mouse sends data. Once again, recall when the mouse is enabled, it's going to send 3 packets at a time. So the first is going to be X, which is going to be the first packet, which is going to have the most significant bit of the X and Y movement, as well as the buttons. And then we're going to have the X movement and Y movement packets as well. So once again, we're doing the same thing with X as we did with the other one. We're taking off the parity start and stop bit so we could actually work with it. And right now we're going to see here that we're going to try to figure out whether or not a button has been pressed. This 1 is always here, so this tells us that the data is good if the 1 is here. And then we're going to see if one of these values is 1. And once again, this is left click, right click, and middle button. So we're going to make sure that the overflow bits, which are these 2, are not true. And then we're going to print it out in binary, and then we're going to say the mouse has been pressed. So now we're going to actually parse the X and Y movement. To do that, we have to realize that the movement is 9-bit 2's complement. In order to actually work with it, we're going to have to, we'll do the same thing with the packet, is to take off the parity start and stop bits, and then we're going to have to get the most significant bit out, and if the most significant bit is 1, then we're going to have to reverse the 2's complement, which means inverting it, anding it to this, adding 1, and making it negative. The Arduino has a 16-bit 2's complement to encode negative integers. whereas the mouse uses 9-bit 2's complement, so that's what we're basically just converting a 9-bit 2's complement encoding to a regular signed int type, as it says right here. And then we're going to print out the x and y movements as well. And that is a program. So now I could get into these functions right here. They follow the algorithm described. So to write to PS2, we're going to set the clock to an output, and then we're going to pull the clock low, and then we're going to delay right here, and that's to wait for the mouse to actually acknowledge, hey, the clock is low. And then we're going to bring the data load to tell the mouse the host wants to communicate. And of course, we're going to release control of the mouse by putting it back to an input, as we described. And now clock is high because of the pull-up, but the mouse is going to pull clock low again. And when the clock is low again, it is ready to communicate. So now we can actually communicate with this loop. So what this does is it waits for a clock to be low, and it will write out from least significant bit to most significant bit while keeping track of the parity. While the remainder of the time the clock is low, we're going to wait here, and then while it's high, we're going to wait here. So when we get back around, the clock is going to be low again, and it's going to be on the next cycle, and we're going to be ready to shift out again. Now we can check for parity, whether parity bit is needed or not, and then we could just pulse the clock again or wait for it to pulse. Now we can release control of the data by sending it back to an input, and we could wait for data to go low, clock go low, data go high, clock go high, and now we're good. So that's how we write, and now we gotta get to how we read. So once again, onside long int, we're going to read 11 bits. That's what the read command does, is it returns 11 bits, not the byte. We have to parse that out as we did in the code above. So we're gonna wait for the clock to go low, and then we're gonna shift it in by shifting it into this variable b, and then we're gonna wait here while the clock is still low, and then wait for it to go high again so that it's low and we read it out again. And then we're going to return b. So it's a pretty simple program. Once again, this is using polling. You could and probably should use interrupts. I don't know if interrupts work with serial, so we'd have to find a weird way to buffer the data. So now we could actually plug in the Arduino, and we should be able to see the data coming in from the mouse. Alright, so just to demonstrate how this works, we're going to reset the Arduino, and it's going to show the data as described. So once again, it took me hours and hours to get this to work, so we're going to go over it. We're going to reset, acknowledge, self-test passed, mouse ID 0, enable, acknowledge. So now, look what happens when I press a button, and the mouse moves a little bit. So what button do you think we pressed? Well, let's look at my hand. Oh look, we did a right click. So right click, again we're moving the mouse. So we did a right click, which is this bit right here. So now let's do a left click, and then you can see this bit is 1. So that's the left click. Let's do a middle click on the scroll wheel, and now that bit's 1. So let's do a left and right click at the same time. There it is, left and right click at the same time. They're both high. So we could do all sorts of things. If we press all 3 buttons at once, that's what it looks like. And let's move the mouse. Let's move it up. And as you can see, if we move it up, the Y will increase. This is the delta Y. So from the last time the mouse sent a packet, it's moved that much. So we moved up all this much. And we can move down. And you can see we're moving down because the delta Y is negative. And now we can move the mouse this direction. Oh look, we're going in the positive X direction. Now we move it in the other direction. Then the X is going to be negative. We can click again, move all around. So yeah, I think I figured out a pretty simple way to get a PS2 mouse to work with an Arduino with no libraries. So thank you for watching.